Dear friends, I am Shashank Srivastava from IGNOU. So in this session I will be discussing with you different things. First of all is the surface hardening. So we start with surface hardening, why it is needed and how it is done. So there are situations that arise in which instead of thorough hardening we need what? We only need to harden the outer surface, and inner can be a little softer, and examples of this case are like gears. So this process is also very much needed. That's why we are studying about this. And surface hardening is achieved through processes, and there are basically three mentioned here. The first is the case carburizing, the second one is the nitriding, and the third one is the induction heating. So steels which have a carbon content of around 0.1 to 0.25, these are the best suited for case carburizing, meaning the first process. So if suppose carbon content in steel is 0.1 to 0.25, we will go in for the case carburizing. So then what we will get? We will get a good combination of tough core, lesser hardness. So we need these things, because if the specimen is completely hardened, so brittleness may also come. So sometimes we need that the inner portion remains tough, and for that toughness it has to be somewhat softer also, and we need the outer portion to be hard so that abrasions and all those don't affect the specimen. So that's why this thing is happening, and we get the tough core and high surface hardness by case carburizing, like that in nickel steel. So this case hardness of 60 Rockwell hardness number with a core hardness of 33 to 38 RC will give us the best result in case of gears. So when we are manufacturing gears, we keep it like this. The core will be hardened up to the point of 33 to 38 Rockwell hardness number, and the outer surface will be hardened up to 60 RC. The case hardness is due to residual compressive stress introduced on the surface by penetration of carbon and nitrogen. So this case hardening is actually taking place by what? It is taking place by the residual compressive stress that are induced, and these are induced by the penetration of carbon and nitrogen gas. So there are different kinds of surface hardening also. So we discuss it here. The first one, what will happen? No addition of any outside element will take place, and only transformation of outer layer to martensite will be taking place. Like we just discussed before this, that carbon and nitrogen are added. So this thing will not happen in the first case. In the first case, only transformation of outer layer to martensite will happen, no addition of carbon or nitrogen. Then the second one will be there. Before that, we discussed the purpose of this, the first one. So the purpose is met, how it is met? By heating the surface by gas flame or causing magnetic induction, so that complete austenite transformation occurs on the surface. So we will subject the surface only to gas flame or to magnetic induction. That way complete martensite will form, and we will not require any additional carbon or nitrogen thing. On quenching, then martensite and the retained austenite formed on the surface, while on the inner side perlite and ferrite will be the main phase. Obviously ferrite is softer, so it has to be there if we want a softer core. Now we discuss the second method. Second method is the method which we have discussed a little bit earlier also, that is the case hardening when carbon and nitrogen were introduced in the surface layer. So this is the second method where foreign things are coming in. In carburizing, the part is surrounded by material or atmosphere which is rich in carbon. That's why its name is also carburizing, because we are giving the carbon atmosphere. And on heating, this carbon will be released and will be further absorbed in the steel. So this carbon is getting absorbed in the steel, and that's why we are getting hardness, and its name is case hardness. Recently, case carburizing is more effectively performed by heating a steel part in the atmosphere or natural gas, or coke oven gas, butane or propane, or the volatilized form of liquid hydrocarbons like terpene and benzene are also used. Volatilized form of alcohol and glycol or ketones are also used. So these are different chemicals. Glycol will have an OH bond, if you know that it represents the alcohol thing, and then ketones are there, so C double bond O. If you know a little bit of chemistry, these are the things which are being used. In these cases, the thickness of hardened layer is proportional to the root of the time of treatment in hour. So the thickness of this hardened layer on the specimen is directly proportional, it is said, to the root of the time. So it will be dependent on the time of treatment. So time of treatment will be very important in this case. So after discussing the two types, with the foreign element one, carbon nitrogen surface hardening, and the other one in which complete heat treatment with martensite formation was there, we move on to the liquid carburizing also. So this thing is also there. Liquid carburizing consists in dipping the part in fused mixture of chlorides, carbonates and cyanides. So there are different types of chemicals. We have chlorides, carbonates and cyanides, and in that a specimen is being dipped. And these baths are maintained at around 840 to 900 degrees centigrade, and they produce a case depth of 0.075 to 0.75 millimeter. So this is the thickness of the case depth on the specimen when we are using this liquid carburizing. And further 0.5 to 3 millimeter of case depth is also attainable if bath is maintained at 900 to 950 degrees centigrade. So the temperature also is very important. Earlier we saw 840 to 900, and if we move higher 900 to 950, then we may go up to 3 millimeter case depth. So it will be much thicker. Plain carbon steel and low alloy steel are the two things which can be carburized in the liquid bath. So not everything can be done. What are the two things here? Plain carbon steel and low alloy steel. We can use this liquid carburizing process. So after discussing the carburizing process, there is one more process, that is nitriding. And how we do that, it is mentioned here. Nitriding of a steel surface is the absorption of nitrogen in the surface. So it is simple. Nitriding name comes from nitrogen, N2, and nascent N2, meaning that is which is fresh from a reaction, is used here and is obtained from ammonia gas. So ammonia atmosphere is required, so that we get nascent N2 from that after reaction. And molten cyanide, sodium cyanide bath is maintained in this case, and the temperature is around 560 degrees centigrade, and it is quite effective in nitriding, particularly if we need a thin case, that is the thickness of the hardened layer is less. Plain carbon steel, actually it is mentioned here that it is not good for nitriding, because what happens, iron nitride is formed. So the plain carbon steel reacts with this nitrogen and forms iron nitride. And why it is harmful? Because this iron nitride is brittle. So we don't need that, because it will lead to fracture. So that's why plain carbon steel nitriding is not done. The steels alloyed with aluminum and chromium and nickel, copper, silicon and manganese, these are better nitrided than plain carbon steel. So wherever this kind of alloying is there, like aluminum, chromium, nickel, all these things are there, then we can go for this nitriding process. Carbon nitriding, nitrocarburizing or gas cyaniding is a process which is similar to gas carburizing also, but here ammonia is also added to carburizing atmosphere. We need ammonia in this process, and this process is actually better than the carburizing process. It gives us better hardened case than carburizing. But again, we have to see what type of steel can be hardened through this process. So in all these things, whether it be nitriding or will be carburizing, we have seen that we need to heat the specimen. So for that purpose we will need equipments, and so we now discuss heat treating equipment. So the main equipment for heat treatment, as we know, is furnace, and in this case there are two major types of furnaces. One is known as the batch and the other one is known as the continuous furnace. And before using the furnace, we need to have an appropriate furnace which can fulfill our purpose. So there's a criteria for furnace selection. And what are the factors that govern this criteria? The first one is the energy consumption, meaning it should be a furnace which doesn't consume too much of energy. We have to optimize that. Then the second point is the manpower requirement for operation. It will be better if we require lesser number of people for the operation of this furnace. Then the third one is the initial cost and convenience of maintenance and repair. So all these factors are there. Economy also comes in. If the cost initially is too high, then also we cannot go for it, and if it requires maintenance and repair throughout its operation, then also we have to see to shift to another type of furnace. Since temperature control and temperature cycle control are very important in heat treatment, like we have seen earlier also, so nowadays electronic and computer controlled furnaces are being used, and they are taking over the older type. Heating in furnace is done by burning oil or gas, or by electric resistance or inductance heating. So this is also one factor which will govern the criteria for selection of the furnace. Then now we see the different types of furnaces. What are the advantages and the disadvantages? So the gas or oil furnace has a distinct disadvantage over electric furnace, because certain products of combustion will be added to the specimen, and it will result in impurity, and different microstructures can be there. Then in case of electric furnace or electric heating, the disadvantage is that it has a slower startup and it is not easy to control. So now we discuss from the two types of furnaces. The first one, that is the batch furnace. And what are the requirements from this batch furnace? We should have insulated chambers. Obviously heat should not be lost, so insulation is needed. Heating system is also very obvious, that you need a power giving system, so heat giving system, that is required. And further we need doors or many doors. And suppose we want to repair or go for maintenance, when it is shut down, then doors are required. And under this category there is the box furnace. So this one is easy to use, and it is simple to construct also, the box one, in various sizes, and it is a versatile one, and it can accommodate several sizes of specimen. Then the second one in case of the batch furnace is the pit furnace, and it is made in form of a vertical pit below the ground level. So you may have seen the different boring machines and all, those also form pits. So this pit is formed in the earth's surface below the ground level, and the parts to be treated are then lowered in this pit. So long parts like the rods, bars, turning shafts, etc., they can be suspended in the space of the pit furnace. So they can be suspended vertically, but if they are suspended horizontally, they are susceptible to distortion. So this should not be done actually. Then further, the third one under this batch furnace is the bell furnace, and it does not have the bottom and is lowered on the stack of parts to be treated. It is like kind of a bell, that's why its name is bell furnace. And the furnace chamber could be round or rectangular. So there are two shapes, it may be round or rectangular. The fourth one in case of the batch furnace is the elevator furnace. In elevator furnace, parts to be treated are placed on a rolling platform. There is a platform which is rolling continuously and in the proper position, and then it is lifted. This platform is lifted to the heating chamber of the furnace. And then what we do, we place a quenching tank directly below the surface. In this way we can save the space and the quenching time also. So after discussing the batch kinds of furnaces, there were 4 types in that category. We discussed the continuous furnace. So this is also very important, because parts to be treated are placed on some sort of conveyor which is continuously moving into the furnace according to programmed heating cooling cycle. So we have the program type of thing where we get the heating cooling cycle, and that is programmed and the conveyor is moving accordingly. The time for loading unloading is greatly saved in this case because it's continuous type, and the handling of the job is also reduced. So these are the advantages of this continuous furnace. So we are saving time here. For high production rate and better control of heat treating cycle, these furnaces are most suitable. Obviously, if it is a continuous process, we will have a high production and we can control the heat treating cycle also in a much better fashion. Then we discuss the salt bath furnaces. Under this category, good control, uniform temperature and high heating rates are obtained as compared to air or gas in case of the salt bath. Like if we were using earlier the air or the gas one, so this one is the salt bath one, and it gives us better control over the temperature. The molten salts or metals have higher conductivity than air or gas, so these are better conducting, so they give better results. And suppose if the salt is non-conducting, then it may be heated from outside or by passing a low voltage alternating current between electrodes placed in the salt. And we don't use direct current in this case because it will result in the electrolysis of the salt, so we use alternating current only. And among metals, lead is commonly used. Lead salt bath is very much used. Wide range of temperature is obtained from such baths. So now we discuss the process of the induction heating. Like we have earlier said that there are different processes. So induction heating is also a process. In this case of heat treatment, alternating current is passed through induction coil. It is similar meaning to the salt bath one where alternating current is used. And this induction coil actually surrounds the part or the specimen which has to be treated. And what happens due to this? Eddy current will be introduced in the specimen and it heats up. Eddy current is a type of waste current which you can study in your electrical subjects, and it is also very much useful in such things where not too much current is needed. So this eddy current is due to the induction only. And what are the advantages? The advantage is that no gas or liquid source for heating is used, and coil can be shaped to surround the part geometrically. So here we are not using any gas or liquid, so chances of impurities are less, and then the coil can also be shaped according to our part, so geometry can be maintained very easily. So here is a figure of this induction heating. The coils are there, you can see in this figure, and these coils normally are made in copper or copper based alloy, and these are water cooled. The coil is also designed for quenching the part after heating, so it is designed in such a way that the part can be easily quenched. For surface hardening requiring local heating, induction heating is suitable. Suppose we want local heating, if we want to harden only a portion of a certain specimen, then induction heating is most suitable. Now we discuss about the furnace atmospheres. Like earlier we discussed about the heating elements and how this takes place and what we require. Now what should be the atmosphere of the furnace? This thing we will discuss. So there are given two types here, salt bath and the atmospheric air, or any of the several gases that are there, that kind is also there. So the disadvantages due to the atmospheric air is that the surface oxidation can take place, tarnishing and decarburization can also take place. So our purpose of surface hardening will not be met. Oxygen can also cause oxidation. So we know oxygen is very harmful because it causes rust and scaling. If there is moisture, then rusting will take place. So oxygen is also very harmful, and these are all in the case of atmospheric air. After oxygen there is carbon dioxide also, so it causes decarburization. We needed carburization in case of surface hardening, but here what is happening, decarburization can take place. So that much important is the furnace atmosphere. We can see that the gas or the this atmospheric air type is not that good. Thin blue film is formed on the surface due to this when water vapor is also present, and this bluing of the surface is done for improving surface appearance. And if we use nitrogen, then it will be better because it provides a neutral atmosphere. So what can be the solution if we are using the atmospheric air? The solution is that vacuum furnaces are used for small and accurately finished parts, and they provide complete safety from effects of atmosphere, because then there are no impurities. In vacuum there are no gases, no oxygen, no carbon, so obvious it will not affect the specimen. So after discussing these things about surface hardening, we now move on to alloy steels. Alloys are very important, and alloy steels are also very important because they meet our various purposes in a very good manner. So what are these? We now discuss. So carbon steels in their commercial forms, actually they contain certain amounts of other elements. Like we have seen earlier also, so many types of elements are there within iron carbon system. Many of these elements will enter the steel from the ores from where it is made. Like iron ore we had discussed in the previous lectures, from that iron is made and then further steel is made. So it is very difficult to remove them, actually, these elements, during the process of steel making. Not all elements are removed. Like elements, these elements, there are harmful as well as the good ones. So the harmful ones have to be removed. All commercial steels containing varying amounts of manganese, silicon, sulfur and phosphorus, and also frequently varying amounts of elements like chromium, nickel, molybdenum and vanadium are found. Alloying elements other than carbon in lesser proportion, example manganese up to 0.8%, silicon up to 0.3%, they are all equal to low alloy or plain carbon steel. So if the manganese is up to 0.8%, the silicon only up to 0.3%, they are known as the low alloy or the plain carbon steel. So further we discuss the alloying elements like the sulfur, phosphorus and silicon. So this is quite, you will find a quite theoretical type of thing, and you can learn from your material also. But here I am giving because whenever you feel like you want certain composition, you can see from the video immediately and it will be easier for you to search. So sulfur and phosphorus, if more than 0.05% in a steel, then it causes brittleness. So that means we have to keep sulfur and phosphorus below 0.05% somehow or the other by processing it. And what about silicon? Silicon, if it is less than 0.2%, it will have little effect on strength and ductility. So it is negligible. And if silicon is less than 0.4% and more than 0.2%, then strength is raised without affecting ductility. So this is a good thing. Strength is also raised and our ductility is also not affected. And if silicon is more than 0.4%, then ductility will be impaired. So the most suitable thing is what for silicon? It should be between 0.2 to 0.4%. Silicon is also added as deoxidizer because it reacts with oxygen and removes it, and that part which does not make silicon dioxide remains in the steel as impurity. So if silicon dioxide is not formed, then obvious that impurity will remain in steel. So now we discuss manganese. So solid solution in ferrite of manganese will strengthen the steel. So ferrite we have discussed, it is the softer type of iron, and if there is manganese, it strengthens that. And this manganese also exists in the form of Mn3C. This is the chemical formula, manganese carbide we can call, and it forms part of the perlite of manganese combination with sulfur, that is meaning manganese sulfide. So in the above range, up to 1% of manganese strengthens steel, and manganese more than 1.5% induces brittleness in steel. So it is given that if it is up to 1%, it will strengthen the steel, and if it is more than 1.5%, it will induce brittleness. So this small range is there only if we want betterment or if we want any kind of change. Excess of manganese is added to melt during the steel making process to bring its level to desired value. It also acts as a deoxidizer. So other elements are also there, some prominent ones we discussed earlier. So what are these other ones? What they will do? They will modify the structure of steel and will improve the properties. Steels with intentional additions, including those steel which contain manganese more than 1% or silicon more than 0.3%, are known as the alloy steels. One particular effect of alloying is that it enables martensite to be produced with low rates of cooling. So earlier we have seen with high rates of cooling martensite was being produced, and due to this high rate of cooling there were cracks. So to avoid this, and this alloying can be very good because it can give us low rate of cooling, so the cracks and all things can disappear. Thus alloying also permits larger sections to be hardened than is possible with plain carbon steel. Obviously, we can harden it more if the cracks are not coming. So alloying can help in that case also, if we want to harden larger sections. So there are other important elements that are alloyed with the steel in small quantities or varying quantities, like nickel, chromium, molybdenum, tungsten, manganese and silicon. Some of these we have discussed earlier. So BCC metals, like the body centered cubic metals, which are these like chromium and tungsten and molybdenum. When these are alloyed with the steel, they tend to form carbides, and these then reduce the proportion of Fe3C in the structure. So these will react with the carbide, iron carbide. So obviously iron carbide will decrease in the structure. Manganese, which has 3 allotropic complex structures, also forms carbide. So like chromium and tungsten and molybdenum, manganese also goes through the same process. Whereas there is a difference on the other hand, the face centered cubic elements. Earlier we had discussed body centered, chromium, molybdenum, tungsten, all these were body centered. And now we are discussing the face centered. These are nickel, aluminum, copper and zirconium. So these do not form carbides. Only the body centered ones will form carbides. So what are the advantages of the alloy steel which we have discussed? We get higher hardness, higher strength and toughness also on the surface and also over bigger cross section. Better hardenability, we have discussed it earlier, so we are getting it better, and retention of hardness is also good at higher temperatures also. Like at higher temperatures sometimes softness comes in, but in this case of alloy steel the hardness is retained even at higher temperatures. So it is that good, and it is good for the creep and cutting tools. We can use them for that purpose, because in creep high temperature effect comes in. So at that high temperature hardness can be maintained, so we can use alloy steel in that case. Higher resistance against corrosion and oxidation also they give, like we have seen with silicon, it forms silicon dioxide, so it removes oxygen, so rusting and corrosion will decrease. So what is the effect of alloying elements on plain carbon steel? We have plain carbon steel, and when we alloy it with different elements, what will be the effect we are going to take up? So they strengthen the ferrite while forming a solid solution, like we have discussed earlier also. The strengthening effects of various alloying elements are given in this order, meaning which one is the best and which one is the worst. So we can see from the top, chromium comes at the top, so chromium can be considered best alloying element because it gives us the best strengthening effect. So moving further down in that order will be then tungsten, then vanadium, further molybdenum, nickel, manganese, and at the lowest point is silicon. Carbides we have seen earlier, so these are formed which are harder and stronger. When we use alloying elements, carbides are formed and they give hardness also and strength. Carbides of chromium and vanadium are the hardest, like we saw that chromium was at the topmost position, so it is best in that case, and it also gives us the strongest, meaning against the wear. So if we have chromium and vanadium as alloying elements of the specimen, the wear will be less for the specimen, and this wear will be less particularly during the tempering process. High alloy tool steel use this effect, that's why we are using in high alloy tool steel. And what does nickel and manganese do? They lower the austenite formation temperature, while other alloying elements raise this temperature. So nickel and manganese will lower the austenite formation temperature. It may come around the 723 degrees centigrade or lower than that. Most elements will do what? They will shift the eutectoid composition to lower carbon percentage. Meaning if we are adding these alloying elements, then the 0.8% carbon eutectoid composition will move towards hypereutectoid. Most elements will shift the isothermal transformation curve to lower temperature. So you may have seen the TTT diagram in the earlier session. So in that what will happen on adding the alloying elements, suppose I am at a temperature of 400 degrees centigrade, then it will shift to 300 degrees centigrade, meaning the transformation curve will be now starting from 300 degrees centigrade, and the effect of this will be that the critical cooling rate will be lowered. That means the so that slope of the line, that cooling rate is represented by the slope of the curve between that this time and temperature. So that slope will be decreasing. Manganese, nickel, chromium and molybdenum are prominently effective in this respect. In what respect? In shifting the isothermal transformation curve to lower temperatures. So now we discuss in a little detail about the effect of the individual alloying elements. We have discussed a little bit in the earlier portion of this session. Now we discuss in detail. So sulfur, first of all, sulfur, what does it do? It is not a desirable element in steel because it interferes with hot rolling and forging also. Thus it results in hot shortness or hot embrittlement. Meaning if the temperature is high and temperature rate is going higher and higher, then it may lead to a tendency of brittleness. That is what is meant by hot shortness. And sulfur is helpful also in some cases. How? In developing free cutting nature. If we want free cutting in a tool, like suppose we are using this alloy steel as a tool, then and as a cutting tool, then we need this sulfur, and it can be up to 0.33% in free cutting steel. So sulfur generally, but is restricted to 0.05% in open hearth or the basic oxygen furnace steel, and to 0.025% in the electric furnace steel. Like we have discussed earlier, sulfur has disadvantageous effects. Mostly, only one thing we saw, that for cutting purpose it can be there. Otherwise, we have to keep it to a very low level. Then phosphorus, and this one also causes some harmful effects like the cold shortness. So as soon as the cooling is happening and there is a certain cooling rate, then the tendency comes in due to this phosphorus of cold shortness, meaning embrittlement will be there. The tendency of the specimen will be to get brittle. That's what we mean by cold shortness, and this will reduce impact strength at low temperature. Obviously, if it gets brittle, so impact strength will decrease. And it is also restricted to the same level as that of sulfur, 0.05 or 0.025. And again, for free cutting steels, it can be added up to 0.12, like in the case of sulfur. But it gives improved resistance to corrosion. It does give this thing, one positive thing about the phosphorus. Silicon. So silicon is present in all kinds of steels in a small percentage, and intentional addition up to 0.5% in steels is there for laminates. Like laminar things are there, layers are there, and why these are there? For limiting eddy currents. These laminates are used in various equipments, like in case of transformers, motors and generators, for limiting our eddy currents, wastage. So in that case, these laminates are made of silicon. So we can see silicon can go up to 0.5%. It also provides toughness, like in the case of springs, chisels and punches. When it combines with free oxygen, like we have discussed so many times earlier also, and forms silicon dioxide, and thus increases strength and reduces the corrosion and rusting effects, and the steel is more sound. But this percentage is only up to 0.5%. So silicon has various advantageous effects on steel. Manganese is present like 1.2 to 1.4% of manganese. This produces extreme toughness and wear resistance, and it also gives us non-magnetic steel, which is called the Hatfield steel. And if it goes beyond this up to 1.6%, then it becomes an ingredient of free cutting steel, like we have seen in the case of sulfur and phosphorus also. And one very good thing it does is that it reacts with sulfur, so, and reduces it. So in case if in your specimen sulfur is more than the required percentage, we can put Mn and it will react with it and give manganese sulfide. But it should be 3 to 8 times than S, then only this reaction will take place. And manganese is effective in increasing hardness and hardenability. So these are some of the good things also about manganese. Further, nickel. What does the nickel do in alloy steel? It increases hardness, strength and toughness while maintaining ductility. So this is a very good property. that it doesn't make the specimen brittle, the ductility is still there, and we get additional things: hardness, strength and toughness. Only 0.5% of nickel is good for impact loads at room and very low temperatures. So this thing is very important, because we had earlier seen the temperature effect in case of the brittleness of different specimens in our earlier sessions. So this nickel will give us good properties at low temperatures for a steel. It is given here. So impact load will increase, impact load resistance will increase at low temperatures when we have 0.5% of Ni. So brittleness will go away. Higher amounts of nickel will improve the corrosion resistance also, but in presence of chromium. So when we want to reduce the corrosion when we are adding nickel, so we need chromium also. It acts like his brother. So I like for an example of a stainless steel. Nickel in a steel will result in good mechanical properties after annealing and normalizing. So after these processes of heat treatment like annealing and normalizing have taken place, then also nickel acts as a very good alloying element. And this particular application we can see in large forgings, castings and structural parts made of Ni steel. So nickel is a very good alloy, is a very good element. Nickel is a very good element for alloying steel. Chromium. Now we see the effects of chromium. Chromium is common alloying element. It's very common, like I have discussed with nickel also. With nickel, combined with nickel, it gives good corrosion resistant properties. So it is used very commonly in stainless steel and corrosion resistant steel, and mostly it is up to 4%, and it forms carbide. Chromium carbide is formed that generally improves hardness, wear and oxidation resistance also at elevated temperatures. It also improves hardenability of thicker sections. So if we have a thicker specimen, then we can have chromium for increasing the hardness and hardenability. Molybdenum. Let's see molybdenum, what effect does it have on the steel. It generally is employed in high speed tool steel. So where we need the cutting and all those purpose and we use steel as a tool, so molybdenum can be very good, because it forms carbide and it gives us high wear resistance, and it also retains the strength at high temperatures. So these are some of the properties which we get after adding molybdenum. So it is added in tool steel and carburizing steel and heat resisting steel also. It gives us heat resistance also, and it increases hardenability like in previous cases we have seen. So molybdenum also gives us hardenability. So molybdenum also assists in improving effects when we use it in combination with manganese, nickel and chromium. So this is also a very good element for alloy steel. We further see some others like tungsten. Tungsten, what it does, it gives us heat resisting steel, and it has the same effects as molybdenum, but in this case larger proportion of tungsten is required as compared to molybdenum. So we can see molybdenum will be better as compared to tungsten. 2 to 3% of tungsten has same effect as 1% of molybdenum. So obviously molybdenum is better. And what about titanium? It prevents precipitation of chromium carbide in SS stainless steel, since titanium is a stronger carbide and former with higher affinity for carbon. So we see in titanium that it has greater affinity for carbon. So this Ti will form the carbide first of all, thus precipitation of chromium carbide will not be there and it will be useful. Vanadium, what good and bad effects it has we see here. It has inhibiting influence on grain growth at high temperature. So at high temperature, meaning grain growth will be lesser, that means nucleation will be more. Carbide possesses highest hardness and water resistance also. So if vanadium carbide is formed, then it is very hard and it will give us water resistance also. So if we are making water resistant products, then vanadium can be used as an element for alloying. It also improves our fatigue resistance, meaning if the number of cycles you have read in the previous sessions about the fatigue, so it is a good thing for fatigue resistance. and it is also a constituent of tool steel, very good constituent of tool steel, and it may be added to carburizing steel also, because hardenability will increase by its addition. So it gives finer things because grain growth is lesser, so obviously it gives better fatigue resistance and all, because the things can be compact. Cobalt imparts magnetic property to high carbon steel. So if the carbon is in the higher range, then it will give magnetic property to steel. And in the presence of chromium, cobalt increases corrosion resistance. Like we have earlier seen that in the presence of chromium, nickel gives us corrosion resistance, so cobalt also does the same. So scale formation is prevented. The next element is the copper, and atmospheric corrosion resistance of steel is increased by addition of 0.1 to 0.6% of copper. Further, aluminium, what does aluminium do in combination with the steel? And nitride steels, 1 to 3% aluminium helps to improve the hardness by forming aluminium nitride. So it will react with the nitrogen there and form aluminium nitride, and thus it will improve the hardness of steel, because then nitride will not react with the steel. And 0.01 to 0.06% of aluminium actually when added during solidification process, meaning the steel forming process, it produces fine grained steel castings. So if we need fine grained steel, then this aluminium can be helpful, especially in case of the castings, steel castings. Boron. So boron, very small percentage, like see how small it is, 0.001 to 0.005, very small, and we have to be very careful about that. And it is effective in increasing hardness, particularly in surface hardening, corroding to. So boron is a kind of element which very much helps in finishing processes because of this effect that it gives us surface hardness. And last one is the lead, and if less than 0.35%, this lead improves the machinability of the steel. So in this session we saw what is surface hardening and what kind of equipments are required in that, like the furnaces, different kinds of furnaces that are being used for surface hardening, and what types of surface hardenings are there, like the carburizing and nitriding, etc. And further we discussed about the alloy steels and various kind of elements. We discussed in detail how they affect the steel and the properties of the steels, and further we will discuss then next things in the coming sessions. Thank you very much.